Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. The next minutes I will talking about deriving representative structural elements for a fatigue approach of WAM components. Let me start with our motivation. Our aim is to perform a high quality fatigue approach of such components. What does it mean? We want to focus on only a few material properties in order to have a good transferability. Also, we have to consider the main influences. I know in case of additive manufacturing, we will have a lot of influences, but just focus on a few of them in order to have 90–95%. That will be enough to get some components like these from the laboratory to the road. Then we need a reliable assessment of different loading situation and conditions. And at least we want to improve the ratio of computational effort and simulation accuracy. How we do it? Therefore, we use the so-called representative structure element. Tomorrow morning there will be a talk just focusing on the ASEs. For today, I think it should be enough to say the classical local approach deals with the material volume, which is ideal, homogeneous, and without defects. But in case of additive manufacturing, we just have more or less structural elements which are inhomogeneous and always have defects. Even if we use really small specimens, it's nearly impossible to achieve really specimens with sound materials so that we can derive suitable properties. What we have to consider if we are talking about ASEs, our measuring values, that means the stress and the strain will always be lower compared to the sound material, as well as our strain life or our stress life curve, we always receive lower values at the same number of cycles. But at the end, when we won't have sound material in our components, so let's start with the ISEs and include also micro geometries within the properties. In case of WAM, we use this coordinate system. That means according to the build direction, we have the force direction. That means the build to force direction has 0 degrees. Or in the other case, we have also horizontal specimens. Then we want to have the advantage of strain and stress control testing, keeping in mind in this case the measurement uncertainty. That means in case of plasticity, it's better to perform strain control tests. And in case of macroscopic elastic material behavior, you can increase the testing frequency without losing information if you go on with force control testing. For the strain control testing, we use the so-called E-cylinder. It's a special developed test rig for low frequency and high quality within the measurement. We can use tactile or optical strain measuring. This depends on the specimens. For higher frequency, we use so-called servo electric driven test facilities, which enables test frequency up to 1000 Hertz. Now start with the first test results from the WAM specimens. Here you see the results for different force to build directions. And as for polished specimens, that's very important. We have taken this specimen from walls, polished them so that we have no influence of the surface. And you can see there's no influence on the stress strain behavior. That means according to the stress strain behavior, we have isotropic material behavior, which is very nice. Also, the fatigue life is not influenced by the direction. That means also here we have an isotropic material behavior, which is nice. Now, how we can describe this strain amplitude to number of cycles to failure correlation, and therefore we use the so-called fatigue life curve. That means we start with the strain control testing, divide them, as it's a standard for strain control testing, in the elastic and plastic parts. And then we can add the force control tests. In this case, we have to transfer them to the strain domain. And then just calculate the parameters of Baskin, Coffin, and Manson, and you will see that this red curve overestimates and underestimates some specific regions, and therefore we use the optimized curve, which is called fatigue life curve, so we even have a better description of the strain amplitude to fatigue. Then go on with the influence of heat treatment. The cyclic material behavior as well as the cyclic structural behavior can be influenced by the heat treatment. That's standard. In case of this material, we have no influence on the strain life, but we have an influence depending on the heat treatment on the stress strain behavior. Then, and now it's getting more interesting, how to describe the influence of the surface roughness or surface topology on the fatigue life. As you can see here, you can imagine that there is an influence if you have polished or specimens or specimens in the build state. This roughness of the surface has an influence on the fatigue life, and also it depends on the direction, which makes it not so nice. Before it was everything was isotropic. Now we have to deal with anisotropic, but I think more important than the anisotropy is to describe the influence in a good way of this structure. Here you see 3 different walls which are built with different exposure parameters. We have a really rough one. I'm not sure if it's just roughness or more or less a topology. Then a better one with a nice pattern, and also for one, more or less a smooth one. At the end, we are not able to measure this topology with our surface roughness measurement system because it was the values was just a little bit too high, the altitudes, so we have to find another way. And here we decided to measure different lines, different measurement distance, and then you get some of these profiles, peak to value. And with our experience in analyzing such profiles in the fatigue, you can imagine that the different parts could be notches. This means this profile is a sequence of notches. On the other hand, you can also analyze with common tools of the fatigue the frequency of these different notches. And therefore, let's start with the notch effect. I think everybody knows that the notch concentration, the stress concentration, depends on the geometry of the notches. That means in this case, the ratio of B, the width, to the height. If you change this ratio, you have another notch impact. Applied this to our profile means it's not enough just to recognize the height, the altitude. You have also to analyze the length. That means the distance of the where this altitude takes part. Here can you see it? We have our profile. We have the delta L and the delta I, and both a ratio. In this ratio, you can count along your measurement distance. Just calculate this ratio and count them, and you get something like this, the peak to value and the sum frequency. And if you do this for the different walls, you see for the red surface, you get for each measurement, you get these different spectra. Then for the blue one, you get another set of spectra, and so for the better one, the green one, you get that one. Now it's important for the fatigue that you find the weakest link. That means we are not interested in this. We need to know the highest value. And therefore, just add this spectra, and you get this one. And here you can see, for the red one, due to the shape of the spectra, you are nearly sure that you have found the highest value. On the other side, the green one looks like you have a nice surface, a population which may be equals to that cos, and some special issues in your surface, in your topology, with a higher value. Therefore, it could be a singularity, and you have to focus it back, trace it back to your specimen or to your wall, or you need some more measurements to be sure that you have found the right surface description. And then how to consider it. And someone of you, I think, have recognized in case of surface, I have not talked about stresses so far, because it's very complicated to define a good cross-section. In case of polished specimens, it's quite easy. You just use the nominal sizes, A and B, but which one you want to use if you deal with specimens in a as-built state? Is it the minimum or the maximum? The minimum you can define after post-mortem. That means after the specimen is broken. So apply this to the component. You have to wait until the component is broken. I don't know if you want to sell them. On the other hand, my way of thinking is just take the nominal dimension, and the rest must be in the properties. Just to explain it in this case, the green one is a stress strain. For the property, for the polished state, it's quite easy to define. If I try to measure the minimum cross-section, I get the blue one, or in case of the maximum cross-section, I get the red one. That means somewhere in here will be my stress strain behavior. But that's not enough for a fatigue approach, and therefore I'm for using the nominal ones. And if you're doing so, you get this stress strain behavior. The black one is derived from polished specimens and constant amplitude tests, and the green one is derived from a specimen which is tested within the incremental step test. And you see, you get nearly the same stress strain behavior. And this is quite nice for the fatigue approach, because you have the same stress strain behavior, and just in the post-processing, you have to concentrate on, you have to decide if you have a polished surface or a rough surface, and you have to decide which of the stress strain curves, strain life curves you have to use. Thank you. I have to thank the European Commission for funding the multi-fund project, my project partners, and you for your kind attention.
Okay, thank you for the presentation. We have time for one quick question. Okay, Professor.
I have one short question. Thank you for a deep presentation, this deep investigation. My question is, when you determine this diagram between the top and valley, peak and valley of surface roughness, this one, a little bit this one,
yeah,
that I am fully agree with this vertical X. Yes, this is dominant factor, but this horizontal X, sumo frequency, from the theory of notches, if one notch exists, is given the fatigue lifetime. Probably this horizontal axis not necessary to
Yeah,
investigate.
I know,
Okay? Yeah,
but you have to find the right one.
okay.
And that's the difficulty. You have to be sure that in your measurement distance, you have these notch. And also, if you want to transfer the properties to a component later on, you have to be sure that your component has distribution like maybe like the red one, that you use the right properties. Otherwise, your calculation will be wrong.
Yes, this is for a large discussion, because if you have complicated axial stress state, this is another factor.
Yeah.
Okay, thank you.